This is a video for continuation of the previous part 2 of a DSP controller TMS320 LF2407 DSP controller IC. In that video part 2, we have concluded with uh, addressing modes. In that, few more addressing sorry a few more indirect addressing examples. You can continue with this video also. Few more new topics we will be seeing in this video. Hello student, this video is about continuation of part 2 video. In part 2 of this topic, DSP controller addressing mode, I have stopped with indirect addressing mode. Few more examples are there for indirect addressing mode that we are going to see now. So, let us take an example for better understanding of this indirect addressing mode. We know that indirect addressing mode is completely depends on auxiliary registers 0 to 7. So, here take this looper is nothing but it's a loop function. We used to mention JNZ loop. Then you will write a loop in the label section. Like that, it's a looper section. And then MAR is nothing but make whatever auxiliary register mentioned in the line as your next current auxiliary register. So, in order to make a auxiliary register as the next current auxiliary register, we will have to use this instruction. MAR nothing but make auxiliary register whatever mentioned in the instruction as a next current auxiliary register. At present, it may be AR0, AR2, AR3, anything it may be. But next, when you're going to use any auxiliary register, this AR1 will be the auxiliary register. So at present, with the help of first line, we have made this auxiliary register AR1 as the next current auxiliary register. This star means pointer. It points to auxiliary register, current auxiliary register. Then the next second line, SACL, nothing but store the accumulator with the content available in the current auxiliary register. So, in current auxiliary register, in the first line itself, it's mentioned that current auxiliary register will be AR1. So, this in the second line, the star points to current auxiliary register. In the first line itself, already we have made that AR1 is the current auxiliary register. So, in AR1, some address will be there. That address contains some value. That value will be stored in the accumulator. Before storing that in the accumulator, here it is mentioned a plus symbol. That means the address available in AR1 will be identified in AR1, and then that address will consist of some value. That value will be incremented by 1. Here it's mentioned increment AR1 by 1. So the content will be added with AR1. That AR1 content will be added with 1. Then that value will be stored in the accumulator. And then here the comma is comma AR0 is mentioned. Nothing but after doing this storing content in accumulator, make AR0 as your at present next current auxiliary register. So for the next line onwards, if you wanted to use any auxiliary register, AR0 is the current auxiliary register. So, and then in the third line, uh, branch to looper at what condition means if that previous AR auxiliary register is not 0. Previous auxiliary register content is not 0. Branch NZ means not 0. Which one not 0? You have to go to the previous line. In the previous line, it's mentioned that AR 0. So you can read this instruction explanation. Current AR 0 is not 0. Then you can, if it is not 0, you can go to looper, as well as at the same time, while checking whether it is 0 or not 0, you will have to make it decrement by 1. You will have to a single instruction will do checking of content of AR not. If it is not 0, go to looper. Similarly, may decrement by 1. So that AR not content will be keep on decrementing. This looping it will be keep on repeating until AR0 is AR0 will become 0. AR0 content will become 0. So, BANZ looper is used to decrement the AR not content, as well as will jump to the looper until the AR not is become 0. I think you all understood the purpose of using this auxiliary register in indirect addressing mode. And the other example for better explanation of this indirect addressing mode, LACC load accumulator star. That means what? Only star is there. That means whatever current auxiliary register content will be stored in the accumulator. Here plus symbol and all it's not there, so you no need to do any increment of the auxiliary register content. And here they are not mentioning any other auxiliary register to be the next current auxiliary register. Just simply they mention that star is nothing but current auxiliary register content will be loaded in the accumulator. Then here the other second line, again you going to store the accumulator content with the current auxiliary register content, but you will have to do 5 times left shifting. That is what is mentioned. The memory content which is available in the current auxiliary register are left shifted by 5 bits, and then it will be stored to accumulator. And then in the third line, load accumulator with what? Star means current auxiliary register, and then make AR3 as your new auxiliary register for further purpose. So this instruction is used for content from AR current auxiliary register will be loaded in accumulator, and make AR3 as your next current auxiliary register. And then example for addition of two number. So here LDP 6H, that means asterisk is nothing but it's a immediate addressing. 6 means how the 6 has came means the second line 300 is there. This 300 divided by 80H, 300H divided by 80H, if you do, you will be getting 6H. That means this 300H 0300 actually, that 0300 is a 16-bit address. In that 16-bit address, a 9-bit is stored in the LDP. So one part of the address will be stored in the data page. That is why after dividing with 80, the 300 divided by 80 will give you 6. That value will be stored in the data page pointer. Remaining value will be available in the next instruction itself. STLK hash 2 300. That means store the number 2 in the memory location 300. So the content 2 will be stored in the memory location 300. Then LACL asterisk 3. That means load the accumulator with the number 3. So the 3 value will be loaded in the accumulator. Then add 300. So Now whatever the content available in accumulator will be added with the content available in the address of 300. So this 300 is not the complete address. Along with the 300, the load data page address, that 6 also is important. Together only will frame that 16-bit. 300 is nothing but it's a 12-bit number. 6 is a 4-bit number. Together, if you join, you will be getting a 16-bit address. That is why that 6 is common in the top. The 300 is not only your complete address. It's a 12-bit address. Remaining 4-bit is nothing but that 6. 6 together 300 will give you a 16-bit address. That 16-bit address will have a value. That value will be added with accumulator. Then the accumulator content is become 5. That is what here they mentioned. The second line, move the value 2 in 300 address. The 300 address is not only 300 address. It is joined with that 6. So you all understood about the various addressing modes of TMS320 LF2407 IC with the various examples. Now we will see the next topic called general purpose input output functionality, GPIO. GPIO pins. GPIO pins means general purpose input output pin. It will be there in the IC. That single pin can work for 3 different actions. In microprocessor and all, we know that AD0 to AD7. AD0 to AD7 means a single pin will work for address as well as data. So how we will separate with the help of ALE signal, address latch enable signal. If it is 1 means that whatever the content comes out of that AD0 to AD7 will be address. If ALE signal is 0, it will be data. Similarly, here general purpose IO pins are having different functionalities. Those functionalities are called splitted as primary function and secondary function. That secondary function is nothing but simply IO functions. Secondary function is simply it will send some data outside and it will receive some data inside. Nothing but secondary function. So what are the various primary functions of this pin? That and all we will elaborately see in the upcoming slide. So at present, how to differentiate whether it is whether the pin is going to work for primary function or it is going to work for a secondary function. Secondary function further classified as in and out, whether it will transfer some data inside from outside to inside the DSP processor, or else it will transfer some data outside. That means from DSP processor to outside the DSP processor. Like this, the signal will be outside. This is inside DSP. Then the data will be transferred outside. If the pin is selected for 0, 0 na, it is moves to secondary function. If it is 1 means primary function. Primary functions are classified as multiple primary functions are there. Those functions and all you will see in the upcoming slides. At present, 0 means secondary function. That secondary function is splitted as input function, output function. That once if you select 0, that means either it is going to work. This switch is moved to 0 means either it is going to work as input pin or output pin. General purpose IO pin. If you select as 1, then it will work for primary function. Once if you put it 0, it will go to secondary function. That secondary function further classified as input and output. That input and output how to select is again another 0 and 1 selection is there. 0 means input function, 1 means output function. So two different switching actions are there. Here first switching action in order to select whether it is a primary or secondary function. If it is secondary function, again another classification is for whether the switch is going, whether the pin is going to work for input or output. So this is a pin multiplexing concept. Pin multiplexing means a single pin will work for multiple actions. And these are all the various address of registers which will do multiplexing operation of various pins, whether to select a primary option, primary function or secondary function. Those things can be configured with this pin, with this registers available for multiplexing. 7090 is the address for MCRA. MCRA means input output mux control register A. This mux control register A is for event manager A, and 7092 is the address for mux controller B. This is common for event manager A as well as for B. So input output mux control register B is common for event manager A and B, and 7094 is the address where you can have MCRC. This MCRC is specially for event manager B. So your MCRA is used for event manager A, and then MCRB is used for event manager A and B. MCRC is used for event manager B. Now we will see what are the primary function and secondary functions. Already we know that secondary function is simply it will act as input output port pins. Simply it will send input data or output data. Secondary functions everywhere. So totally what are the ports available? These are all up to totally 8 pins are there in port A, and then port B also is having 8 pins. So it will act as simply sending in data or out data. Secondary function is not having multiple options, but primary function of the pin. Once if you put the switch in primary function by making that switch is in one position, then what are the various functions are available? The pin can be configured as serial communication interface transmit pin. You can use serial communication interface receiver pin. You can use, or external clock frequency timer. We can use capture one or quadrature pulse circuit, or capture two quadrature encoder pulse two. These pins details and all you can understand with the next slide. At present, I will explain. I will give you the full form of these things. Capture 3 unit, whether to use or not, we can use. We can select with the fifth bit of this input output mux control register configuration. Similarly, if you wanted to generate 6 PWM, some programs you may require to generate 6 PWM. Then this pins and all used, this pin and all you have to utilize for generation of 6 PWM. So in mux control register A, pin number 6 to 11 will play a role for generation of 6 PWM. Similarly, if a program, if they are asking you to write a program with the help of timer one, means time generate a PWM using timer one, means then in this register mux control register A, this 12th bit will play the major role. Similarly, if they are asking you to generate a PWM, single PWM using timer 2, means 13th pin will play the major role. 13th pin of mux control register. These are all you should remember, because in the upcoming slides we will be writing a program using a timer 1 or a timer 2 for generation of single PWM. Then this mux control register 12th pin and 13th pin MCRA 12th pin or 30th pin will be utilized. And similarly, one more program is there. That program is for generation of 6 PWM. Then this pin number 6 to pin number 11 will play the major role. So these things you should remember when I'm going to explain about the program for generation of 6 PWM or program for generation of single PWM using timer 1. Similarly, this timer direction A, this timer direction A, in the upcoming slide, when I'm going to explain the GP timer operating mode, you can use this. This one will decide whether the timer has to work for up counting or down counting. So, depends upon whether the bit is 1 or 0. If it is 1 means it will do up counting. If it is 0 now, it will do down counting. So that up counting and down counting of a counter or timer will be decided with the pin number 14. Timer direction A pin. Then timer clock input A pin. This thing for input clock frequency of a timer can be decided with pin number 15. Similarly, for MCRB, this will be common for event manager A and B. Various options are there, but here port C will be used for again. If the option is selected as secondary option, here port C and port D will be utilized. That to port D only only D0 is there, but remaining things and all it is reserved for future updation. Primary options are if you go through, you will able to understand primary option of MCRB. These things are not much utilized for writing the program for PWM generation. So we are not going to see this in deep. Similarly, MCRC is used for event manager B. In event manager A will generate PWM1 to PWM6. Event manager B will generate PWM7, 8, 9, 10, 11, 12. So this also will generate 6 PWM, but this PWM number and all 7 to 12. And similarly, in MCRA will use timer 1 and timer 2. MCRC will use timer 3 and timer 4 because timer 1 and timer 2 are relevant to the event manager A. Timer 3 and timer 4 are relevant to the event manager B. MCRC is used for event manager B. Remaining pins and all, it is similar to your MCRC. And similarly, event manager A is having 3 capture unit, and event manager B is having 3 capture unit. Capture unit is nothing but to hold the value in order to check what the at present your counter or timer is calculating, or what the at present timer is showing value that can be captured and can be displayed, or for any calculation purpose or any manipulations, the capture unit will capture the content of timer and it will show the count value. Already I've explained this event manager A and event manager B when I'm explaining this architecture of TMS320 LF2407 DSP controller. It consists of interrupt logic, two general purpose timer, 3 capture unit, already I told you, and then PWM circuit is used to generate to control the speed of the motor. And deadband generation unit. This deadband generation unit is most important. With a proper diagram, I can explain this deadband generation unit in the upcoming slides. Similarly, 3 capture unit, 3 compare unit, 3 capture units are there, and quadrature encoder pulse circuit. Quadrature encoder pulse circuit is used to convert sense the speed of current speed of motor, and then it will convert that as a pulse. That pulse will be given to the timer in order to count the number of pulse. That after the count of number of pulse, uh, the processor will understand what speed at present the motor is running. So you can, with the help of quadrature encoder pulse, we can measure the speed of the motor by calculating the number of pulses output from the quadrature encoder pulse. The quadrature encoder pulse circuit will convert uh, actual speed of the motor into number of pulse. These block diagram already I've explained in the part 1 video. This is a block diagram of event manager B. Previous one we have seen event manager A. Clear explanation is given in the part 1 video. And various event manager A interrupts, that is that and all you can see. Here you can use this address, vector address, timer 1 count. These compare interrupt, then similarly timer 1 period interrupt. These are all used for generating interrupts when the timer 1 is counting. If you wanted to stop the count, this interrupt address it will go. If you interrupt this interrupt, it will jump to this address, and then it will execute a program to interrupt the timer content. These are all various event manager B interrupts. But these things we are not going to use for program writing for generation of PWM signals. So I'm not showing much concentration on this this interrupts of event manager A and B. Now we will see general purpose configuration, general purpose timer configuration. So let us consider why you need this timer for PWM generation. Let us take a waveform. Two signals are there. One is this black color line, first signal, and then the second one is red color line. That first signal black color line is uh, will be started with a value of 0 starting point. This is the starting point of the black color line of first signal. Here it will start with 0 0 0 0. Count value is initially 0 0 0 0. So timer 1 count value will be 0 0 0 0, and how long it will increase means, if you see period value means how long the waveform will be generated up to it reaches from 00 to 4000. Here it's mentioned 4000. So timer 1 period register consists of a value 4000. So from 0000 count value to 4000 it will count. Who will count? Timer will count. Timer will check the period value register whether it will initially the timer value will be incremented from 0000 to 0001. Then it will compare whether the 0001 is equal to 4000. No. Then it will increment to 2 whether it is equal to 4000. Like that it will keep on increment. Once the timer count value reaches 4000, it will compare with the period value, timer 1 period register value. Period register value is loaded with 4000, and timer 1 count value also it's become 4000. So if both are equal, it will stop generating the it will stop incrementing the signal more than 4000, and it will come down again. It will start a new signal. Again one more black color line signal will be generated. Like this it will be keep on executing, keep on generating this signal. Only one pulse of waveform I am showing here. So then we will see the next signal called red color line signal. That red color line signal is your second signal, which is drawn at the magnitude of 800. This point is 800. Actually, the black color line can move to 4000. In 4000, you can, before moving to 4000, you can have 800 line also. So, this red color line is directly drawn at point of 800. So, once both the signals are overlapping at two different points, this is first point and this is second point. So in the two different point, a pulse has to be generated. When both the signals are overlapping each other, signals will be generated. So overlapping each other means how you can understand, how you can identify overlapping means both are equal. How you can identify both are equal with the help of compare circuit. So you need timer in order to calculate from 00 to 4000. Then similarly you need a compare unit to compare that 800, both the signal are reaching 800. So this compare unit is there. Similarly, once the compare unit reaches, that period register content and the timer content reaches, obviously one signal has to be generated. So you need a PWM generator. So once that both the signals are reached, overlap each other at 800 in two different point, a pulse will be generated. Whether you need this kind of pulse, that means initially it is at 0 and it will go to high and then it will maintain high and then it will go to low. So from low to high signal you required or high to low signal is required, can be programmed with general purpose timer control register. With this you can get whether you required a first signal or second signal. First signal means low to high signal or high to low signal can be configured with the help of general purpose timer control register. Also mux control register also used for this. Those things, how to get this low to high signal or high to low signal, these things you can see when I'm going to explain the program and explanation of that registers. Here we will see example. Let us take, we know that event manager A consists of two timers, timer 1 and timer 2, and event manager B consists of timer 3 and timer 4. With that only this example is going to work out. Let us consider when x equal to 2. X equal to 2 means here you include that x equal to 2. Here if you include x equal to 2, it's mentioned TXPR. That means timer 2 period register. So timer 2 you're going to use here. Timer 2 period register. Nothing but timer 2 you'll be using. Then here y equal to 1. Y equal to 1. This first condition is separate 1. Second condition is separate 1. So at present your x equal to 2. So this one is nothing but timer 2 period register I am using. Then y equal to 1, nothing but timer 1 period register. So this is timer 2 period register. This is timer 1 period register. You can see this timer 2, then this one timer 1. Okay, so both are having both are ready to work. Which one you going to use for your PWM generation, that you can select with this mux control register. This mux control register, circuit is controlled by TN con register. TN means here n value they have mentioned. N value is nothing but 2. So your timer 2 control register. So Tn means you can, for first condition, when x equal to 2, y equal to 1, that means timer 2 period register, timer 1, period register, both are given as the input for the mux control register. Your n will be 2. So this mux circuit will be controlled with the help of timer 2 control register with the help of 9th bit. That is what here mentioned, 9th bit. So once if you see this timer 2 control register 9th bit, you can able to understand why this bit whether this bit is used for selection of timer 2 or timer 1. Selection is can be done with the timer 2 control register or not, that we will see once if you see the um, register. Then here we know that x equal to 2. So timer to compare register we will be using timer to compare register. So timer 2 will be used to compare the count value. Count value means already I told you period register is having 4000. Now the timer will start counting from 00 to whether it is reaching 4000 or not. So here the timer period register is 4000. Let us take your timer 1 value is 4000. So that value is selected by mux control register. So 4000 will come here. This compare logic now as an input of 4000. One input is 4000. For comparison purpose you required two inputs. So other input is this timer counter register tx here. Tx na x equal to 2. So your timer 2 will start counting. So your timer 1 period register you are using, and timer 2 control controller timer 2 control register you are using. So counter register you are using. So what will happen, this timer 1 timer 2 counter will start counting from 0 1 2 like that. From the top 4000 will come. Once this bottom one reaches 4000, and the top one also already 4000, both are aligning together. So both are having same value, means top value is 4000, bottom value 4000. Top value is period register value, bottom value is counting value. Once the bottom value starting from 0 to 4000, once if it ends at 4000, both values are same, then automatically it will start generating a synchronous waveform or asynchronous waveform. That also you can select, that you can see in the register selection. Then it will start generating a PWM signal. So from the top 4000 is loaded, from the bottom you will be incrementing the count value 0 1 2 3 like that. Then once compare logic understood that 4000 has reached in both the condition, it will start generating a PWM. Here x is there, that means TX PWM, timer to PWM will be generated. This is for example of how the PWM is generated. Here GPT con A/B GP timer control register also used for generation of PWM. Here why this GPT con control register is used for generation of PWM, you will understand once if you see the program explanation. So this is a program for generation of PWM using timer 1. So here what are the registers are used? Mux control register A. So already we have seen what is mux control register, and what are the primary pins, what are the secondary functions, all those things we have seen. And I have explained about loading data page Y0E1 and Y0E8, all those things I have explained in the previous video. And then here in the block diagram of generation of PWM signal, GPT con A and B is used, RB is used for GPT con means general purpose timer control register also is used for generation of PWM signal. That also you can see in the program. In that register you are going to load a value 6042. That 6042 if you load, what will happen, what and all you are selecting, those things you can see in the upcoming slide. Then this timer 1 count value initially 00 for that black color line waveform, black color line waveform first signal is generated. Initially it starts with 0 0. That is why the timer 1 count value is initially 0 0. Then at what point of time you going to compare first signal and second signal? It is at 800. At 800 only the PWM pulse will be generated. Then what is the use of 4000? This 4000 is the total period of the signal will be first signal, how long the first signal has to be generated, that total period. Here that 4000 signal and 800 signal, these two is get compared, and at that point only the PWM is generated. At 4000 the PWM is not generated. Once that 4000 signal, first signal, and 800 signal, second signal, these two signals are overlap at 800. So at that moment only, that dotted lines I have mentioned, that point we have taken. In that area only the PWM signal is generated, not at 4000. Remember this. At 4000 it will stop generating the black color signal. Again it will go to 0, then again it will start incrementing from 0 to 4000. Like that it will be keep on repeating. Then timer 1 control register. In the program, timer 1 control register also is used in order to control the timer 1 operation. Whether timer 1 has to do continuous up counting or continuous down counting or directional up counting. That up counting, down counting operation and all I explain clearly. And here that 9042, if you load on timer 1 count register, what will happen? Those things you will I'll explain in the upcoming slides. So here with this timer operation, we can generate ADC, we can generate a pulse for starting the ADC conversion. ADC means analog to digital converter start. So with the help, let us take an example. After 20 seconds, I wanted to start a analog to digital converter. So then again 20 seconds means I will load a value 20 in the period register. Count timer 1 count will be started incrementing from 0, 1, 2, 3 like that. Once the compare logic becomes both are equal, that time ADC will be started. So this timer operation can be used for generation of PWM signal, also to start analog to digital converter also it can be used. Now we will see what are the various general purpose counting operation of a general purpose timer. Counting operations are called as stop and hold mode. First option is stop and hold mode. Let us take, we all know that stopwatch. We will be having a stopwatch in our watch or in mobile, or a special device is there for stopwatch. If you press a button, it will start counting like 1, 2, 3, 4, 5, 6, 7, 8, like that it will count. And if you press the button again, it will hold and it will show the current value. What is the value at present it shows. During running race and all, we will be using this kind of counter or timer in stop or hold mode. Stop or hold mode means what? Initially it will start and it will increment, and if you press the same button, it will stop and it will show what is the current value. This is nothing but stop or hold mode. Second mode of counting operation is continuous up counting mode. Continuous up counting mode is, with the diagram I will explain. Third one is directional up down counting mode. Continuous up down counting mode is fourth one. So we will see one by one. Now first one already we explained. Second option is continuous up counting mode. This is the example diagram for continuous up counting mode. At present the period register, if you mention period register with 4 means that value will be decremented by 1, 2, so that decremented by 1 to reach the exact value of counting. If you want to do counting of 4 number, that means it will start with 0. So you need 4 number now, 0, 1, 2, 3. So it will go up to 3 counting. If you have mentioned 4 means it will do 4 counting, but the final value will be 3. 0, 1, 2, 3, 4 values. Then it will not, this operation is continuous upcounting mode. So continuous upcounting mode means it will not do any down counting. So 0, 1, 2, 0, 1, 2, 3. It will do up counting. And then once that count value count value and period values are reached equally, because what I have mentioned, period value is 4. Period value will be decremented automatically by 1 to reach to 3. So at present your period value is 3. So once from 0 to 3 it reaches, immediately it will come to 0. Then again, because again it will start from 0 to up counting, 0, 1, 2, 3, like that it will do up counting. Nothing but it is continuous up counting. It will not stop it will not stop doing a counting operation, 0, 1, 2, 3. Then it will not do down counting, 0, 1, 2, 3. Like that it will keep on counting. Here, for example, they have mentioned the period register with 2. That means it will do 0, 1, 2. That means here actually they have given us 3. That will be decremented by 1 default. So that you will be getting 2. So it will count for 3 number, but it will not show 3 value. So 0, 1, 2. Then here you can see again it will not do down counting. Again it will reach 0. Then again it will start up counting. 0, 1, 2, like that it will start counting. So it is a continuous up counting mode. Then next one, directional up down counting mode. Directional up down counting mode is nothing but this T directional A or B, one pin or one bit is most important in this directional up down counting mode. When this T means timer direction, you can decide. So timer direction, whether event manager A or event manager B, that is what here A or B. Timer direction E or B, event manager A or B. So event manager A means what are the timers available? Timer 1 and timer 2. Event manager B na timer 3 and timer 4. So we can select which direction the timer 1 and timer 2 under event manager A has to count, which direction, whether it's up direction or down direction. That can be done with the help of this additional bit called DIR/A/B pin. If it is 1 high, you can see that here the timer direction A/B. Here they have mentioned timer period register as 3. So it will start counting up to 3. So 0, 1, 2, 3. While counting 0 to 3, this time direction pin will be in high position 1. So it will do up counting because it is in high position. Timer direction A or B pin will be in high position 1. You can see this line. Then once again up to this area it is 1. So again it will start doing up counting only, 0, 1, 2, 3, 0, 1, 2, 3. Once the time direction pin is becomes low, here you can see initially it is in high position. Now the time direction pin bit will become low. So in this area, when the time direction pins and all it is under low condition, it will do down counting only. That is what here it's mentioned. When the time direction A or B is low, it will do down counting. So the direction of counting can be decided with the help of this time direction ARB pin input. So you can see here, it started counting 3, 2, 1, 0, and then again it will not going to do any up counting because the time direction bit is what? It's low. So again it will do down counting only. Once if it reaches 0, again it will be down counting. Again it will start goes to 3, then it will do down counting. Once if you do if you change the time direction bit too high, then it will do up counting, it will not do down counting. So direction of counting, whether up counting or down counting, can be decided only with the pin TDIRA/B, time direction A or B pin. Then next one, continuous up or down counting mode. Continuous up or down counting mode is here we are not going to use this timer direction pin. Here what it will do? It will do continuous up and down counting. It will start with 0. If time period register is consist of 3, it will count up to 3. 0, 1, 2, 3. It will do up counting. What is the title? Continuous up counting / down counting. So first it has done up counting 0 to 3. Now it will do 2, 1, then 0, down counting. Then again if the period register value is changed to 2, it will do up counting to 0, 1, 2. Then it will start doing down counting 1, 0, then 1, 2, like that. You will have a continuous up counting and down counting. Here you can't see any timer direction pin. So timer direction pin is low or high. It will not worry about up counting or down counting. The direction of counting is not controlled by that time direction A/B pin, but remaining and all similar to your directional up down counting. This is your timer 1 control register bit configuration. Here TX con is mentioned. TX means X can be mentioned with 1, 2, 3, 4. Anything you can put. Time 1 means it is timer 1 control register. 2 means timer 1 control register its address is 7404. Timer if you put X as 2 timer 2 control register 7408. Then 3 means which comes under event manager B, its address is 7504. Then 4 means timer 4 7508. But the operation of these registers is similar for all the timer 1 to timer 4. Now we will see each bit why we are using, what is the purpose of using this bit. As we have seen in the program of generation of a single PWM pulse using timer 1, in timer 1 control register, you can see in the program we will be substituting a value called 9042 in timer 1 control register. Now we will put that 9042 value in this 16-bit value. This is nothing but 16-bit value. This 9042 is a 16-bit value. 16-bit value. This 16-bit value can be loaded inside this register. How to load? 9 means what? 1001. That 1001 will be loaded from 15th bit to 12th bit. So 1001. That 1 will be 15. Then 00 will be 14 and 13th bit. You can see this bit, those bits and all. 15th bit will be 1. Then 14th bit will be 0. 13th bit will be 0, then 12th bit will be 1. 1, 0, 0, 1. You have to write in this. Then 0. 0 na again 4 zeros are there. So 11 to 8, you have to write 0, 0, 0, 0. Then fourth one, 4 means 7th bit to 4, 4th bit you have to put 0, 1, 0, 0. Here 0, here 1, here 0, 0 because 8421 logic. Then 2 means 0, 0, 1, 0. So now we will see the explanation of this 9042. If you put in this register, how it will help us to generate a PWM signal with the timer 1, because this will be useful for understanding of the program. So this one you can change for timer 2 as well. If you wanted to change the program for generation of PWM with the timer 2, then the address will be changed as 7408. Timer 2 control register address will be changed as 7408. If they are asking you to generate a PWM signal with timer 3, the address will be 750404. These are all the hint to write a program with some other register, timers. So now we will see the complete explanation of that. Initially we have substituted in 15 and 14th bit 1 0 will be there because 9 is there. So 1 0 0 1. So 1 0 in 15th bit 1 will be there, in 14th bit 0 will be there. So check the explanation. What they are using? 1 0. 1 0 na operation is not affected by any emulation suspend. Emulation suspend na, if you are programming the IC, already some program is there. In some other memory location, you are writing new program. But you are going to generate the PWM pulse with the already available program. While including the some other program in some other memory location, due to some malfunction, loading of the second program is interrupted. But already available program only is going to use to generate the PWM signal. Then this interruption of loading of second program in some other memory location should not disturb generation of first PWM, first program execution and PWM generation. So that is why 1 0 is mentioned that operation means PWM generation is not affected by emulation suspend. Then 13th and 12th bit. 13th and 12th bit already what I told you, 9 means here 15 and 14 is 1 0. Here 0 1. 13 and 12 will be 0 1. So 13 is 0. Even if it is 1 also no issues, because it is reserved for future purpose. So your 12th bit will be 1. 12th bit is 1 means 12th bit is 1, then 11th bit is 0. So 12 and 11 will have 1 0. That means it is going to do continuous upcounting mode. Why continuous upcounting na? In the diagram which I have shown for generation of PWM pulse, a black color line, first signal is keep on incrementing. You can see that it is not going to do any down counting and all. It is going to do up counting only. So that is why 1 0 is selected. You can see that signal, first signal. This is the first signal, continuous up counting mode. So if you require some other thing like this, some other waveform, continuous up counting as well as down counting, like this is up counting and then it is down counting. So this will have continuous up / down counting, then you will use 0 1 as 12 and 11th bit. But according to this program, according to this waveform, you need 1 0 to be put in 12th and 11th bit, and then 10 and 9th bit will be 0 0 only. 10 and 9, 10, 9, 8, everything will be 0 0 only. So that 0 0 is deciding the clock frequency. Whatever the clock frequency, that will be divided by 1. So that means same clock frequency only you are going to use. You are not going to divide the clock frequency. So it requires whatever the frequency you are applying, that frequency only it will operate. Then next one. So till now we have substitute the value of 90. That means 1001 and then 4 zeros. This explanation you have understood up to 8th bit you all understood. Then 7th bit. 7th bit is 0 because you're going to load 4. So here 0, then next bit only, 6th bit only it's 1. So 7th bit is 0. 7th bit is 0. Actually the 7th bit is used for whether you're going to use own timer or you're going to get help from the nearby timer. That means let us take timer 1 and timer 2. Two timers are there. Timer 1 always will use own bit to control whether timer 1 if you want to stop or you want to start, its own bit can be used to start and stop. It is not depends upon any other timer. But event manager A consists of timer 1 and timer 2. Here timer 1 always will use own bit to start and stop. But timer 2 can be start with its own bit similar to timer 1, but also it can able to start with the help of timer 1 bit. Timer 2 can be start with the timer 1 bit, but timer 1 never be start with a timer 2 bit. Always timer 1 will use its own bit to start and stop, but timer 2 can be controlled with the help of timer 1 bit. So are you going to use own bit for doing this operation, or are you going to get help from timer 1? This timer 1 timer 2 operation is for event manager A. Similarly, in event manager B, timer 3 will work like a timer 1 and timer 4 will work like a timer 2. So your timer 4 can be start and stop with the help of timer 3, but a timer 3 never be start with other timers, only it will start with its own bit. So that you're going to select with the bit 7. So in bit 7, we know that 0 is the value we have loaded. So 0 means timer 1 I am going to use. So use own timer enable bit. You can read the explanation for one. If you put what will happen, the explanation is given clearly. Then next one, bit 6. Bit 6 is for timer enable. Whether you're going to enable the timer or disable the timer. In between also you can stop the timer. That will be decided with the help of bit 6. But bit 6 is loaded with 1. That means you're going to use a timer. So you have to enable the timer. Then bit 5 and 4 according to the value you can see what is the content we have loaded. 9042 we have loaded. That means 00 we have loaded in 5 and 4 bit. 5 and 4 bit means 0 0. That means I am going to use internal clock frequency only. Internal clock pulse only. I am not going to use any external clock or quadrature encoder pulse circuit also having some clock. That clock will work in some other frequency. Whether are you going to use your timer with quadrature encoder pulse clock or internal clock or external clock, that can be decided with the help of this 5 and 4 bit. And then are you going to use are you going to reload the value of a timer compare register at what point of time? You will be comparing that 4000 signal with with 800. So that time only it will compare. So one or else similarly, when the counter is 0, it will again start counting. Like that, that operation and all can be decided with the help of this third and the second bit. You can load the value and you can check which option is selected here. Similarly, uh, disable timer compare operation. The compare operation, timer operation is different, the compare operation is different. Timer will do counting operation. Whether the compare operation is required or not, that will be enable or disable, that we can do here. 1 means enable, 0 means disable. Then similarly, how I have explained with the 7th bit, similarly their 7th bit is for timer control register, whether you going to control with one bit or different timer bit, that will be selected with bit 7. Similarly, here that is control register. Here we are talking about period register. Timer period register are you going to get from nearby timer, but timer 1 always use its own period register only. Timer 2 only will get help from timer 1 period register. Similarly, timer 3 in event manager B will use own period register only, but it will not use period register of timer 4. But timer 4 can get help from timer 3. Now we will see explanation of general purpose timer control register A. Its address is mentioned as 7400. This general purpose register in the single pulse PWM generation, we have loaded 6042. You can see the program for understanding of this 6042. Why we have loaded 6042 for generation of PWM, we will understand now. 6042. Now load that 60 here. 6 means 0, 110. So initially 0 we are loading. So already it's reserved. In 14th bit 1 we have load. Then 13th bit we will load 0. Then in 12th bit and 11th bit, whatever maybe it is reserved. But any of that 6 will be loaded. 6 means here 0. So 0, 110, nothing but 6. So we will see the explanation of 14th and 13th bit. 14th bit, whether timer 2 status you can read using this bit. Whether if it is 0 means timer 2 is doing counting downwards. If the bit is showing 1 and timer 1 is showing doing counting upward. So timer 2 you can timer 2 status can be checked with the help of this bit. So up counting or down counting you can check it. Double one. So that means 14th bit is 1 and it is doing upward counting only. Then timer 1 13th bit also is doing upward counting only. Timer 2 actually we are not using the program, but in case if you use timer 2, that also as we do up counting. That is why for safer side we have selected counting upward for this program. In some other program there will be a chance of doing counting also. That also can be done. Then 12th and 11th bit will be no use because it is reserved. So here 6 already loaded, then 0, 9 and 10 bit and all, it is also 0. 0 means 10 and 9. No event is going to start ADC. Already told you the timer operation either to start analog to digital converter or for generation of PWM. But in the program 6042 is loaded. in order to generate PWM signal, not to start any analog to digital converter. So I no need to start analog to digital converter. That is why that 00 is selected as 10th and 9th bit. Then 8 and 7. This is for 8 and 7 is uh, for timer 1, whether timer 1 is required to start ADC, that will be checked with this. Again 00 it's mentioned, no even starts ADC. Again I am going to generate only PWM signal. So here up to now what I have included, it's 6, then here it's 0. Now I have to load 4. So here 0, then your 6th bit will be 1. If it is 1, if it is 1 na 6th bit is 1, enable all GP timer compare output. That means you're going to have a comparison between two signals like this signal. Two signals you're going to compare. So compare operation should be there. That is why here I have done enable. Or if you don't want that, you can do disable. But according to 6042 in the program, here I have mentioned 1. Then 5th and 4th bit no use. Then 3rd and 2nd bit you're going to load 0, 0, 1, 0. That means what? 2. So that 0010 here 00 is nothing but in 3rd and 2nd bit. We will see in the next slide. 3rd and 2nd bit will be 00 and 1st and 0th bit will be 10. So 0, 0 and 1, 0. So 00 na your what kind of signal you going to get? PWM pulse like this pulse. So initially low, then it reaches to high, then it will be low. So initially low, then high. So timer 2 I'm not going to use. So I'm not going to select a perfect thing for whether it is low or high. That is not an issue. I'm going to use timer 1 in the program. So I need active eye signal. Active eye means after the that both signal are gets compared, I required a pulse for active eye. This is active eye. Then so this is a concept of getting that loading 10 in the bit 1 and 0. Then GPT can be, this is for if you use timer 3 and 4, you can see that timer 3 and 4, it is similar to your GPT con A. If you use event manager B, if they are asking you to write a program with event manager B, then you should not use in the program GPT con A, you have to use GPT con B. Similar pins are available. Then timer 1 period register address and all you have to note down, because timer 1 period register only we will be using in the program 7403. This address will be used for loading a value, that 4000 the program. So this address is important, kindly note down. And then compare unit block, how the comparison will be takes care. Compare unit block, how the PWM signal is generated. Here TZ is mentioned, TZ counter. So a counter is going to counter. Z means here two options are there. Event manager A na Z will be 1. Event manager B na Z will be 3. So let us consider timer 1. So timer 1 counter value will be there. It will be start counting. Then here compare register will be there. Here the compare value will be there. These two will be, both will be compared with the compare logic. Then it will be given as a signal for PWM circuit. Then the PWM circuit will start generating the PWM, whether you need this kind of pulse, low to high or high to low. This can be decided with the help of action control register. Action control register. PWM circuit will generate PWM. But what kind of pulse will be selected with the help of action control register. For better understanding of this action control register, you must know what are the pins, what are the bits available. If you put 1 on that, which will be disabled, which will be enabled, 0, which will be enabled, which will be disabled, all those things you can understand clearly once if you see the action control register completely. So I have given an example program for generation of 6 PWM. What is the need of generation of 6 PWM? That also you must know. Take an example of BLDC motor control. Here BLDC motor is connected for, actually this is BLDC, but it will work with AC only. Even though it is mentioned as a DC, but it will not work with the DC supply, it will work with AC supply. That to 3-phase AC. For 3-phase AC, inverter is there. This is 3-phase inverter. 3-phase inverter will be having 3 legs. 3 leg means this is first leg, and this is your second leg, and this is your third leg. First leg, second leg, and third leg. So each leg consists of 2 switches. Each leg consists of 2 switches, T1 and T4, and then second leg consists of 2 switches, third leg consists of another 2 switches. So here AC supply is given, and then filtering action takes by the inductor. Then this is your rectifier, which will convert input AC into DC. That DC is again filtered with the capacitor. So here DC will be available. That DC is converted as AC with the help of this 3-phase inverter. This 3-phase inverter switch will be controlled with the help of controller. This controller, you can see it is generating 6 pulses. You can see 6 arrows. This 6 pulse PWM will be given to the 6 switches, so that you can control the motor easily. So I think you all understood why you need 6 PWM generation for any circuit, power electronic circuit. This is a power electronic circuit. This circuit you can draw for any explanation of PWM generation for 6 PWM generation for motor control. Here, what you require is most important, deadband generation circuit. Deadband generation circuit is nothing but let us take general operation of this inverter. Here, first T1 switch and the bottom this switch T2, T1 and the bottom. This is T2, 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 and this one T1. That means one from the top in the first leg and one from the bottom in the third leg. These two will be turned on. Usual procedure, if you know power electronics inverter operation, you can easily understand this. T1 and T2 will be first has to be turned on. Then T3 and T4, second leg top switch and first leg bottom switch will be turned on. This is the second operation. So at that time the T1 and T2 already turned on switch should be turned off. So before turning on the second pair of switches, first pair of switches should be turned off. So we can't say at what time the T1 and T2 is getting first pair of switches will be turned off. So we should give some dead time. Dead time means all the switches are in off condition. That means at the same time T1 first pair switch and second pair switch should not be in on condition. But first pair switch and second pair switch both can be in off condition. But both cannot be in on condition, first pair and second pair. So what we will do is that when you're going to switch on the second pair of switch, we have to wait for first pair of switch to be turned off. So when the first pair of switch is getting turned off, while going first pair of, let us consider first pair of switches turned off. Now only I am going to start turning on the second pair of switch. Now only I am going to turn on. That means at present that second pair of switch is in off condition. This period of off condition of both the pair of switches, that means all the pair of switches are in off condition, nothing but deadband generation, deadband period. That means all the switches are in off condition. Why? Means first pair of switches is giving some kind of signal for motor to run. Second pair of switch will give some other signal for motor to run. But both the pair of switches are in on condition. Motor will not run properly. So you should have some delay time to turn on second pair of switch before after turning on for turning off first pair of switch. So some dead time will be there. That time is required for to control any motor. So for that we need deadband generation circuit. For this deadband generation circuit, what are the registers we are using, all those things you have to see. So that because this deadband circuit is completely used for 6 PWM generation. You can see here PWM1 to PWM6 it's mentioned. So this deadband generation circuit is loaded with 08E8. While seeing the control deadband generation control register, we will load 08E8 value in that. Then we will understand what we will be using. Then here are you going to use normal PWM signal or space vector PWM signal? Space vector PWM signal we are not going to give for this inverter. So this mux controlled will be selected with the help of COM-CON A. COM-CON A means compare control register A. Compare control register A 12th bit. 12th bit is used to select whether you need normal PWM signal or space vector PWM signal. With the bit 12 we can select. Then bit 11 and 13 is used for COM-CON A. 11 to 13 is used for synchronous waveform or asynchronous waveform. All those things you can see once I explain compare control register A. And for 6 PWM generation, DPT-CON A, DPT-CON means deadband control register A also is required. Similarly, whether you need this kind of pulse or high to low or low to high pulse will be decided with the help of action control register. continuation of this topic you can see in the next video. Thanks for watching this video.